we want to look at, therefore, a way to make sure that the height of the tree is not order n, but is at most order log n. And such trees, such binary search trees are called balanced binary search trees. And so we want to today understand how can we design a balanced binary search tree data structure. So these are sometimes called self-balancing binary search trees, because we'll see that as we are inserting and deleting into or from this data structure, we will uh, we will change things, we'll modify the structure in a way that the height always stays order log n. So we don't have to come in and periodically rebuild the tree as a balanced tree. It's going to be self-balancing after every operation. So the agenda for today, therefore, is to discuss one or possibly the simplest type of self-balancing binary search tree. So we're not going to be taking lead code style problems today. So this is more along the lines of the trees foundation videos, an extension of where I stopped there with binary search trees. Any questions about the agenda or anything so far? Okay. Now, one of the things I want to do is to write everything down as we are designing this data structure, so that you have these notes for consulting later. And one small change I want to make in the convention is that I'm going to assume the height of any tree to be the number of nodes along the longest path from the root to any leaf. So normally when we talk about height, we say that different nodes are at different levels. This is level 0, this is level 1, this is level 2, this is level 3. And so the height of the tree is 3, the maximum level number. Now instead of that, I'm just going to slightly change the convention and say that for this class, the height is going to be defined as the number of nodes along this longest path. So instead of 3, it's going to be 4, 12, 18, 15, and 17. And I'm doing this because it will be easier if the height exactly matches the number of nodes to which we are comparing our value when we are searching or inserting or deleting anything, right? So the number of comparisons along in the worst case along this path is going to be exactly 4. So it doesn't make a difference to the argument, but it'll just make the analysis a little easier if we assume that the height is the number of nodes along the longest path from the root to any leaf. Okay. So there is one type of balanced tree that we have designed before, and that was in the sorting foundations. We built a binary heap in the form of a conceptual tree which had a perfectly symmetric shape like this, right? We call this a complete binary tree. Now a complete binary tree ideally would have everything filled till the last level, right? If the last level is full, in that case there would be exactly 2 to the power h nodes at the leaf level. There, of course, h was defined as the level number. So starting from level 0, assuming that we go down up to level h, At level h, we would have exactly 2 to the power h nodes, since the number of nodes in each level is the next larger power of 2. So, can we design a balanced binary search tree with this type of structure? Well, the last level need not be full, because if the last level is full, we are assuming that the number of nodes we have is exactly of the form 1 plus 2 squared plus all the way up to 2 to the power h. Right? In other words, this is just 1 less than some power of 2. So if n is exactly 1 less than some power of 2, then only we can hope to have a perfect structure like this. But that's not going to be true, because our collection is dynamically changing, so there's no reason to assume that n is exactly of this form. So we need not, n need not be of this form, since we have a dynamically changing structure here. So the last level, so in a complete binary tree, what we have is everything up to the last level, right? The internal nodes, all of these are full. And then we said that the last level is full starting from the left end. So whatever nodes there are in the last level, they're all packed on the extreme left. The last level partially filled from the left end. And this was actually the um structural property that a heap had satisfied. That is, the overall shape of the tree always looked something like this in general. So the question is, can we build a binary search tree that has that kind of shape? That would be the natural direction to go in. So we want this kind of structural property, and we want the binary search tree property to be satisfied. So in the case of a heap, we wanted this structural property, and in addition to that, we wanted a heap property. The heap property was that the value in every node should be less than the value in its two children if it's a min heap, and more than the value of its two children if it's a max heap. So that was the heap property. But the structural property was that we need this kind of structure. So let's go in that direction for a moment and see what happens. So let's assume we have um, a binary search tree with elements 2, 3, 4, 5, 6. What would it look like if it had to have the shape of a complete binary tree? So this kind of blue shape is called a complete binary tree. So if we want that kind of structure, we have 5 nodes in our tree. So by definition, the root is going to be one node. There are going to be 2 nodes at the next level. So we have 3 so far, and we have 2 more left. So both of those nodes have to be children of the left node here. So this has to be the structure if we have 5 elements in our tree. Now the binary search tree property also needs to hold, which means for any node, the value in the left subtree should be smaller than it, and the value in the right subtree should be bigger than it. So if we want that, then there is only one way to populate this tree. We know from the foundations again that when we do an in-order traversal of uh, a binary search tree, we are going to be reading the values in increasing order. So that means the smallest value has to go here, because that's the node we will first, whose vertical protrusion we'll first touch when we are doing the boundary walk. The next node we'll look at is this, so that has to have the next higher value. This should have 4, 5 should be here, and 6 should be here. There is no other way There's no other alternative if you want to have a complete binary tree as the structure with the binary search tree property. So, so this does look fine, but let's see what would happen if we now insert a 1. Even if there was a way to initially build this kind of a binary tree, is it possible to implement an insertion operation in a way that is um, that's going to take no more than order log n time? So to insert a 1, we will first search for a 1. So we start from 5. 1 is less than 5, we come down here. 1 is less than 3, we come down here. 1 is less than 2, we come down here. And so to insert a 1, we will need to uh, we were to follow the same insertion procedure from earlier. We will end up inserting the 1 here. Now this satisfies the binary search tree property, but it violates the structure of the complete binary tree. um, it violates that shape. So the new shape, after whatever rebalancing we have to do, should be such that there will be 6 nodes, which means the shape has to be something like this. And again, by following the in-order traversal route, 1 should be here, 2 should be here, 3 should be here, 4 should be here, 5 should be here, and 6 should be here. Right? That's the order in which we will touch each node from below. So what would it take to go from this structure on the left to this structure on the right? Notice that all the pointers have to be changed. So 2 has 1, 2 dot left is 1. So in this case also, I guess 2 dot left is still 1, but it's it's still a modification that we are doing while at the time of insertion. 2 dot right is null here. Um, so 2 had no children earlier, now it has 2 children, 1 and 3. 3 had 2 children here, 3 has no children here. So both pointers of 3 have been updated. 4 had no children here, 4 has 2 children here. Again, both pointers have been updated for 4. 5 had 2 children here, 5 has no children here. And 6 had no children here, 6 has 1 child here. So every pointer has actually changed. So let me actually remove this and make it dotted so that it's clear. It's clear that it is still a modification that we are doing. Okay, so the total number of modifications that will be involved in inserting and then preserving that complete binary tree structure, in the worst case, you can say order n. So for this reason, this is not the type of shape we want to go towards. Because if we restrict ourselves to the shape of a complete binary tree, then it's not going to be possible to readjust things in log n time. Even if the final height is log n, too many nodes have to be moved around to achieve that. So Abhishek asked, in the recursion problem set 1, how many binary search trees with n nodes? In that question, it seems like there are many ways to create a binary search tree from n nodes. Why do you say that there is just one way here? What's the disconnect? Oh, so here we are trying to impose a particular shape on the binary search tree. We are saying we want a binary search tree that is balanced. So and balanced in this particular way with this particular structural property, that every level except the last level should be completely filled, and the last level, to whatever degree it is filled in from the left hand. If we impose this requirement, then there's only one binary search tree that is possible. But in that question you're talking about, there is no balancing requirement. It's just, how many different ways are there to construct a binary search tree. So that, there'll be a combinatorial explosion there. Any other questions? Okay, so for that reason, we will need to try something different here if we want to build a new data structure. So the structure that we are actually going to move towards, so let's actually get our inspiration from this failed attempt here. We saw that it's too stringent to have a requirement like um, every node is going to have two children if it's an internal node, and or maybe just one child if it's a leaf node, but then that leaf node has to be the only leaf node with one child. Um Even if we observe and restate the property here as saying that every node, so for every node in this kind of a shape, or in this kind of a shape in general, the the height of the left subtree can be at most one more than the height of the right subtree, right? That's another attempt we can make here to come up with this property, but we know it's too rigid. For every node, the height of the left subtree is at most one more than the height of the right subtree. So let's relax this property a little bit and say the desired property we want is for every node the heights of the left and right subtrees differ by at most one. So this time we are allowing, this is a little more flexible than the previous diagram in that we are allowing the right subtree, sorry, the height of the right subtree to be slightly bigger than the height of the left subtree, which will never happen if it's a complete binary tree structure. So another way to say this is the mod of the height of the left subtree minus the height of the right subtree is less than or equal to 1. And you might have seen some problems um, earlier in your trees class which use this property as the definition of a balanced tree, right? For example, the problem where you're given a sorted array and you want to uh, build a balanced binary search tree out of it. But the definition, if you note there, was basically this. Now, this was actually historically, the first type of balanced uh, binary search tree that was built by a couple of Russian mathematicians. Their names were Adelson, Velsky, and Landis. And so, uh, for that reason, the name of this type of balanced binary search tree is AV and L. Right? AV for from the from the last name of the first of those mathematicians and L from the last name of the second. And this is actually the simplest balanced binary search tree to analyze, which is why I decided to focus on it. There are other types of balanced binary search trees like red black trees, 2 3 trees, B trees, 2 3 4 trees, splay trees, and so on, um, which are all harder to understand. So, but even though this is the simplest, the it is still complicated enough that you are not going to be asked to code up the operations for an AVL tree in an interview. So for that reason, we just want to understand how rebalancing is done. If somebody asks us, we should be able to at least explain it algorithmically, but there's almost no chance that we'll have to implement it. And you'll see why, because there are just going to be a number of cases to think about. So, I mean, it can be a programming assignment in a data structures course, but it's not something that is doable within 15 or 20 minutes. So that's the reason it's unlikely to be asked in an interview. Now this property of the height of the left subtree minus the height of the right subtree, the absolute value of that, this is technically known as the balance factor, or you can say the degree of imbalance, right? The degree of imbalance should be less than or equal to 1. So that means the balance factor can be either +1, can be 0, or it can be -1. These are the only 3 values allowed for it. So let's look at a few examples of trees and see which of them satisfy this particular balance property. So here we call this the height balance property, since we are trying to balance the height. There could be other ways of trying to balance a tree. Maybe you want to balance the number of nodes in the left and right subtrees instead of the height, but that leads to more complicated types of trees. So we'll focus on the simplest type here. So let's take this example. So what's the balance factor for all of these nodes here? So let's start from the leaf, and again we're going to use the number of nodes as the height. So for this leaf level node, the height of the left subtree is 0 because there is no left child. Height of the right subtree is 0. So the balance factor is 0. For this node, the height of the left subtree is 1 because there is one node in it. The right subtree is 0, and so 1 minus 0 is 1. So it's +1. This node, well, actually let's look at this first. This also has a balance factor of 0, and this 6 has a balance factor of -1 because height of the left subtree is 0, the height of the right subtree is 1. So the root node has a left subtree that has a height of 2 and a right subtree that has a height of 2, and so the balance factor is 0. Now the balance factor of every node in this tree is either 0, -1, or +1. So this is an AVL tree. Let's look at the last tree actually. So in this tree also all the leaves have a balance factor of 0. When you look at the two internal nodes, the heights of their left and right subtrees are 1, and so the balance factor for them is also 0. And so the root of the overall tree has a left subtree that has a height of 2, a right subtree that has a height of 2. So the balance factor is 0. So the balance factor is 0 everywhere, which basically means that everything is perfectly balanced. This is like a complete binary tree with even the last level full. Now let's look at the middle tree here. All the leaf nodes will again have a balance factor of 0. This node has a balance factor of 0. This internal node also has a balance factor of 0. Um, let's look at the 4 here. So the height of the left subtree for 4 is 2. There is no right subtree, so the right subtree has a height of 0. So the balance factor for 4 is plus 2. For 6, there is no left subtree, so the height of the left subtree is 0. The right subtree has a height of 2. 0 minus 2 is minus 2. The balance factor there is minus 2. For the root node, the left subtree has a height of 3. The right subtree has a height of 3. The balance factor is 0. Now this tree has two nodes that are imbalanced or unbalanced. So for that reason, it's not an AVL tree, because every single node has to have a balance factor of uh, with a modulus value of less than or equal to 1. So here are a couple of more examples of uh, trees with the balance factors also written next to each node. So as you can see, this particular tree is an AVL tree since the balance factors are all allowed. This is not an AVL tree because the root node has a left subtree that has a height of 3 and a right subtree that has a height of 1. 3 minus 1 is 2. So this is not allowed in an AVL tree.